Should be great. Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Santosh Nagarakatte, Professor and Undergraduate Program Director, Department of Computer Science from Rutgers University. The title for today's talk is Correctly Rounded Math Libraries in the Age of AI. Dr. Santosh obtained his PhD from University of Pennsylvania in 2012. His research interests are in hardware software interfaces spanning programming languages, compilers, software engineering, and computer architecture. His papers have been selected as IEEE MICRO Top Picks papers for computer architecture conferences in 2010 and 2013. He also received the NSF CAREER Award in 2015, ACM SIGPLAN PLDI 2015 Distinguished Paper Award, ACM SIGSOFT ICSE 2016 Distinguished Paper Award, and 2018 Communications of ACM Research. Highlights paper for his research on LLVM compiler verifications. His PhD student David Menendez dissertation on LLVM verification was awarded the 2018 ACM SIGPLAN John C. Reynolds Outstanding Dissertation Award. His papers on correctly rounded elementary functions have been recognized with the ACM SIGPLAN PLDI 2021 Distinguished Paper Award and the ACM SIGPLAN POPL 2022 Distinguished Paper Award. His PhD student Jay Lim's dissertation on correctly rounded elementary functions were also awarded the 2022 ACM SIGPLAN John C. Reynolds Outstanding Dissertation Award. He was selected as an ACM Distinguished Member in 2023. Dr. Santosh, it's a great honor to have you as part of our webinar series. Thank you so much for taking the time this morning, spending time at UND, for this webinar. The floor is yours, and thank you. Let's see if you can able to share the screen.
Yeah, thanks, Prakash, for the introduction. So let me just share my screen. Can you folks see the screen?
Yes.
Awesome. I'm excited to talk to you about some of the new results that we have in building the world's fastest and correct math library. And I thank Prakash and Gavin and folks who sent me the invite. And so I know this is a webinar series, so I'll try to make it as interactive as possible, like give you moments to pause and sync in the data and other things. So math libraries are things that every programmer uses as part of their day-to-day activities. And we assume them to be correct. It's like the plumbing of your ecosystem, right? As long as all your pipes, all your faucets are working, no one bothers about them. And when there is a leak in your house, that's when you're running after a plumber. So math libraries are like the plumbing of the computing ecosystems. And so the moral of the story that I want to take away right now is we are building a lot of fancy castles with very weak plumbing infrastructure, and now bringing down your the next cool AI infrastructure with a small plumbing leak is very easy. So that would be the takeaway, and I will reinforce it as I go along in the talk. So just to get you started, I'm showing a snippet of code. This is in the C programming language, but this is the core of most of your algorithms for machine learning. Underneath, NumPy or your PyTorch runs these algorithms to find gradient descent. So what is happening on this code? So you have a float variable, you're incrementing, you have an increment, which is 0.1f, and then you're computing a result. And in this code, all you're doing is you're running the loop 10,000 times, and you're adding the increment. So imagine this increment to be the step when you're finding the gradient of your function that you're trying to optimize for your neural network training in your backpropagation algorithm. So if all you're doing is adding 0.1 10,000 times, the result should be 1,000. And I have an assert just for pedantic exposition purposes. If the result does not happen to be 1,000, abort the program. And so since this is a webinar, I can't ask you a question. If I ask, how many of you think this program actually aborts? Typically, when I given this talk, about 50% of the audience say, oh, this program should work as is. All you're doing is 0.1 times 10,000, it should be 1,000, and this program should never abort. But in reality, this program aborts all the time. And this is because there are two reasons. One, your increment is 0.1f. A 0.1 is not exactly representable in a binary floating point representation. As a result, there is some rounding. So there is some inaccuracy, and the result is not going to be 1,000. The second reason that happens is because you're comparing a floating point value to an integer. So the compiler will have to promote at some point, either promote the integer to a floating point and then compare, or demote the floating point to an integer and then compare. So there could be loss of precision there. There could be some loss of some error happening. So in general, this program aborts. And so the moral of the story, this is the core building block of our AI infrastructure, and not many people can reason about it. And this is where, like, if there is one takeaway from this talk, if you are interested in machine learning or AI, you should pay attention to underlying foundations, how these systems are built to have a fruitful career. Okay, now coming back, why did I get interested in building elementary functions? These are e power x, ln of x, and so on. So for a long time, when I started my career as a assistant professor at Rutgers long time ago, 12 years ago, my primary focus was on making lightweight formal methods. Like, you have compilers such as LLVM or GCC, which are 7 million lines of code. And as with any software that is large, it's going to have bugs. But compilers are such trusted pieces, we wanted to make sure they're correct. And to make them correct, like, testing is one way to go, but the alternative way is to use formal verification. And typically, to use any of these formal verification tools, people needed to have a formal methods PhD. So my focus during my initial faculty years was to make lightweight formal methods a reality for compiler development. As part of it, like, if you want to make any formal methods a reality, you need to have automation. And if you have done any computing course, you know, doing reasoning about any non-trivial property automatically is undecidable. So you have to, you have undecidability barrier coming in for automation. So you need to make approximation, you need to identify a subset where you can do a good job. So that's when we realized, like, what are the most buggiest pieces of a compiler? So it turns out peephole optimizer, every compiler has a peephole optimizer. What is a peephole optimizer? It does like basic low-level optimization, such as like you have a times 2, it can be replaced by a shift operation, a left shift by 1. So so that the code runs faster on your machine. See, these are local function level optimizations, typically mathematical identities. So why do they have bugs? These have been known. There's a fantastic paper by John Reger where he shows that, like, this has been a source of bugs in almost every compiler that you have. Now you may be wondering, why are these peephole optimizers, such as like mathematical identities, buggy, right? So if you look at any mainstream compiler, these are compilers for C and C++, and they tend to have undefined behavior. So, and the C++ and C languages have very permissive semantics, saying that if you have undefined behavior, the compiler can just set your house on fire, right? Like, or can do whatever it wants. So it just provides semantics for well-defined programs. So this interaction of undefined behavior and mathematical identities is a recipe for disaster. So there are lots of bugs. And what we wanted to do was we built a domain-specific language, which was both a specification language and an implementation language. Our intention was the developers would write these optimizations in our domain-specific language, and we automatically generate C++ code that does the optimization after we prove that the optimization is correct. So we built Ally in collaboration with John Reger, Nuno Lopez, and my student David Menendez long time ago. And now, 10 years hence, this Alive tool is being actively used by almost every company that works on LLVM. And GCC also has similar DSLs to check correctness. As part of it, my student primarily initially focused on integer optimizations. And then we realized, even when compiler developers don't want to do anything with floating point, a floating point is an approximation of a real number, they get this optimization wrong. So initially, we did the bit precise verification of floating point optimizations. That's just like you just want to follow IEEE 754 identities and check they are correct. And it turned out even when compiler LLVM developers did not want to do anything with floating point identities, they were wrong. They were changing the sign of 0. So William Kahn, a Turing Award winner, has a fantastic paper saying why if you change the sign of 0, it's going to introduce discontinuities in elementary cuts. So that was good. Then there is this demonic mode of optimizations called fast math. So effectively, like what does fast math do? It treats any real number identity as a floating point identity and optimizes the code. Why is this important? Like, for example, floating point arithmetic is not associative. If you want to do vectorization or if you want to execute the code in parallel, you need associativity. So what compilers do is that turn a blind eye towards the lack of associativity and treat it as treat like it to be a real identity and then do the optimizations. So we knew about fast math, we didn't know how to deal with it. But my student was completing his breadth requirement for his PhD, and then he had to train a machine learning classifier, a support vector machine algorithm on a curated data set. And then he had this idea. His training was taking like some K hours. He wanted to accelerate it. He just ran the training with fast math. Same algorithm, same data set, same number of iterations. But the accuracy of the resulting algorithm tanked substantially. Like it was getting like 50% accuracy when it was earlier. It was having 80+% accuracy. So now we wanted to debug. So now you have a model which is which is compiled with fast math, and it is producing inaccurate results. And we wanted to, and then there is a model which is trained without fast math. It's producing an accuracy of 80+%. You wanted to debug it. There are no tools around. So we just built our own tools to debug such things. We called it shadow execution. So what is our oracle? Our oracle is like you execute the computation with real numbers, and then we substitute every floating point operation with a real number, and then compare the floating point execution lockstep. Where is the floating point execution diverging from the real number execution? So this is shadow execution. And it turned out the first place these errors occur are when you call these elementary functions like e power x, the math library functions. And that's got us started on this journey towards building correct math library functions, correct and fast math library functions. So now, what are the kind of errors that you see in mainstream library with math functions? So for example, if you use GCC or Intel's LibM, these functions, the math libraries provide implementations of e power x, tan of x, sine of x, cosine of x. All these functions are incorrect in the sense they don't produce the oracle correctly rounded result. They are like off in the last digit. So instead of producing your grade to be 99.95, it will produce 99.90. So will this matter? So what we discovered in our experiments or in the story that I told till now was, even though this may appear inconsequential, these get amplified by further cancellation and various other things and result in catastrophic behavior. So the moral of the story is we wanted to build correctly rounded functions. So if you think, oh, Santosh is preaching to the choir, like, and he has an agenda to build math libraries, that's why he's making this case about new machine learning algorithms not being robust to rounding. There is a fantastic talk by a machine learning researcher, Ali Rahimi, in 2017. His paper won the Test of Time Award at NeurIPS, which is a premier machine learning conference. Somewhere in the middle of the talk, in this keynote, he says his team, he leads a large production team, and his team, as one of his team members, changed the rounding mode of a training of the deployed model from round to nearest to round to 0. Sometimes round to 0 is very easy to implement, just truncation. So in TensorFlow, he changed the rounding mode to round to 0, and the accuracy of the model tanked from 90% to 25%. So they had to immediately take action and fix it. So these numerical issues, especially with elementary functions and others, are so common when you're building a machine learning infrastructure that runs like large-scale training. So our goal was to build, okay, here, this looks like a really compelling problem. 6 years ago, we set out, oh, let's build correct and fast math library functions. Okay, so just to get you started and so that we are all on the same page, what is a correctly rounded result? Okay, so we don't have real numbers in the real world. So we only have finite precision representations. That is a floating point representation. So let's call V1, V2, V3 to be values that are representable in any floating point representation. When you write a float, it's a 32-bit representation. V1, V2, V3 are 3 representable values in a floating point representation. For the purposes of this exposition, these are adjacent. And there is your real number line. And if you have an elementary function such as ln of x, so the fact that it's an elementary function, the output of an elementary function is going to be an irrational value. So it cannot be exactly represented as a rational number. Any floating point value is a rational number. You cannot be exactly represented. So it will be that blue star. And now what do you need to do? You use the best known algorithm for computing ln of x, and you compute it with real numbers and compute this star, blue star. And then you do one final rounding according to the rounding mode to the nearest value. In this case, the blue star happens to be very close to V2. And if your rounding mode is round to nearest ice go to even, then the blue star will be rounded to V2. So if you produce V2 for input x1, then V2 is the correctly rounded result. To summarize, you use the best known algorithm for ln of x, and you compute it with infinite precision. So there is no rounding whatsoever in any of the other steps. And then you did the one final rounding to the target that you have. That is the correctly rounded result. And the holy grail of developing correctly rounded math libraries is to produce this correctly rounded result for all inputs. So if you produce such correctly rounded result for all inputs, this is called as a correctly rounded math library. So now let's look at why prior techniques, like there are 4 decades of work on approximating elementary functions. Why don't they produce correctly rounded results? So a common technique to approximate any function, any mathematical function, is to approximate it with a polynomial. And when you are approximating with a polynomial, you don't want to reason about floating point or anything. You just take the real value. You take a real analysis class, you generate a function approximation that approximates the real value such that you minimize the maximum error across all points in the function. So approximating a function with a polynomial is feasible only over a small domain. In this figure, you can see I can use a polynomial to approximate ln of x between 1 to 4. Anywhere else, like it will be very hard to approximate. So the first step you need to do when you have a function that you want to approximate is to reduce the domain, the set of values that are given to the input, to a small domain, small region. This process of reducing the input from a large space, if you look at a 32-bit floating point, the largest value that you can represent is approximately 2 to the power of 128. And the smallest value that you can represent is 2 to the power of minus 149. So this is a very large range, where it can represent very large values and very small values. So doing polynomial approximation over this entire domain is very hard. So what do? You reduce it to 1 to 2. So take an input x, use some mathematical identities, and then reduce it to a value, your x dash, to between a value 1 to 2. And then do polynomial approximation over this small domain 1 to. Okay. So, and to generate the polynomial approximation over the small domain, what are you trying to do? Over the small domain, you're trying to minimize the maximum error across all inputs. So this is called as the minimax approximation. And if you have taken real analysis, this is minimizing the L infinity norm. Okay. And then finally, what do you have? You have a reduced input in the domain 1 to 2. You use the polynomial approximation, you get the output y dash. And now you need to produce the produce the output for the original input x. So you compensate the result produced so that you produce the result for the original input x. That process is called as output compensation. To summarize, everyone does functional approximation using the real value of the function. Then they do it over a small domain with argument reduction. And then they do a polynomial approximation with minimax approximations. And then they do the output compensation to produce a result for the original input. All these three steps, like a range reduction, polynomial approximation, and output compensation, happens with floating point. It has numerical error. Now let's consider an input x1 where the output of ln of x1 is very close to the rounding boundary. So what is the rounding boundary? If you have two values v1 and v2, and my rounding mode is round to nearest, the midpoint is the rounding boundary. If I go slightly past the midpoint, I'll change where I round. So the midpoint is the rounding boundary. If the real value of ln of x is very close to the midpoint, the amount of error that you can have with range reduction, polynomial approximation is shown by the gray box in the figure. If you have any additional error, now it's going to change the rounding decision. You're going to round to an incorrect value and you're going to have a wrong result. And this is precisely why mainstream libraries produce wrong results. So first of all, you don't know how much precision you need to simulate so that you reduce this error. So this is known as a tablemaker's dilemma. And the second thing is you need to generate polynomials of very large degree and do your range reduction, output compensation, and a polynomial approximation with with significantly higher precision, so that your numerical error is limited. And this was the state of the art before we started working on it. So our idea when we started this project is, okay, so there are the thousands of researchers who have worked on this domain, worked on this problem, and have built slow oracles. In the sense, like today, there are libraries such as MPFR. You give it an input, it will produce the correctly rounded result. It takes 2 hours, let's say. Like I'm exaggerating here. It takes a long time, but produces the result, correctly rounded result. So we have oracles that are slow, but I cannot use them in my training, machine learning training, because it will be very slow. Just producing e power x takes hours. I have to do billions of such e power x computations every cycle, right? So to have any progress in training my large LLM. So I cannot use them for my actual practical purposes. So, but there is an oracle out there. So our idea is, rather than approximating the blue star, which is the real value, directly approximate the correctly rounded result V2. Okay, so effectively what I'm saying is, like, use the oracle that people have generated, which are slow, and split the problem of generating correct and fast math libraries into 2 parts: the task of generating the oracle and the task of generating fast implementation when someone gives you the oracle. So if you buy the idea that there is an oracle, like I know what is the correctly rounded result for each input. Now I'm going to generate polynomial approximations that directly approximate the green circle rather than the blue star. So this is the first key idea in the LLVM project. Think like a computer scientist. So rather than approximating the real value on a machine, you only have finite precision values. So you have a finite number of them. So directly approximate the correctly rounded result. If you buy this idea that you can directly approximate the correctly rounded result, there is an interval of values around the correctly rounded result, such that you produce any value in this interval that rounds to V2. So now for this example, what is this interval? It's from the midpoint of V1 and V2 to the midpoint of V2 and V3. This interval, you produce any real value in this interval, that it will round to V2. This is the freedom that LLVM project has. Okay, for a given rounding mode, like there is an interval of values around the correctly rounded result, so such that you produce the correctly rounded result, you produce a value in this interval. So this is the value of directly approximating the correctly rounded result. Just to re-emphasize the fact, like I said, some time ago, look at the freedom that we had with other methods. Like the gray box here was the freedom, and that was very small with prior techniques. But now, if you come back to the LLVM approach, where I'm directly approximating the correctly rounded result, the freedom is much larger. Okay, so now what do we need to do? So we are in the RLLVM project, we are directly approximating the correctly rounded result. And then when I'm implementing a library for 32-bit, I'm going to implement, when I'm building a library for 32-bit, I'm going to implement the library in 64-bit representations. So there are a lot of values between V1 and V2 that are representable in 64-bit double precision. And there is an interval of such value. So that is your freedom to generate polynomial approximations. Now, what is a polynomial? So just to summarize, what is a polynomial? A polynomial is P of x1 for a particular input. Has to be P of x1 has to be less than or equal to h, which is the upper bound, and greater than or equal to L, which is the lower bound. So effectively, by approximating the correctly rounded result and identifying this interval, we have created a linear constraint, which is P of x1 is less than or equal to h, is greater than or equal to L. And what is P of x1? It's C0 plus C1x plus C2x square and so on. If I'm generating a polynomial of degree D, there'll be D such terms, D plus 1 such terms. And what is now known in this polynomial? The x's are all known. Those are the inputs that are given. What is not known are the coefficients C0, C1, C2, C3, so on. So to summarize, what are we going to do? We are standing on the shoulders of giants. We assume there is a function and then oracle available. So given a function, f of x, in this case, it could be ln of x, and a target representation, in this case, let's say 32-bit, and a rounding mode that we want to generate for, like round to nearest. That's the most commonly used rounding mode. So we are going to enumerate every possible input, and we are going to use the oracle and generate the correctly rounded result for each of those inputs. Okay, and that's what the graph shows here. And then we are going to compute the rounding interval around the correctly rounded result, such that any value rounds to the correctly rounded result that I have. Once I generate the rounding interval, I can forget about the correctly rounded result. Each rounding interval induces this constraint, P of x1 for an input x1 should be less than or equal to h1 and greater than or equal to L1. So if you're looking for a 32-bit floating point representation, there are 4 billion such constraints. So each polynomial is of the form C0 plus C1x and C2x square. So this entire 4 billion such constraints boils down to solving a system of linear inequalities. Where there are 4 billion such inequalities, we solve this linear system. There you go. You have a polynomial that satisfies the rounding interval constraints for all inputs, and we have a correctly rounded elementary function. So again, to summarize, the first key idea in the RLLVM project is to directly approximate the correctly rounded result. And if you directly approximate the correctly rounded result, there is an interval of values around the correctly rounded result. That is the interval between the two rounding boundaries. You produce any value in this interval, you get the correctly rounded result. And now this interval induces a linear constraint on the output of the polynomial. So if you have a representation with k bits, there are 2 power k such constraints. In the worst case, you solve them, you have a correctly rounded math library. This was the essence of the RLLVM project that we started on. So what we have accomplished with this is for a given function and a given representation and given rounding mode, we can generate a correctly rounded implementation. So I was excited when I built this library. Then I started talking to mainstream developers. They said, this is cool. Like, we have generated really fast math libraries, right? But they said, oh, if you look, there are 5 rounding modes in the IEEE standard itself. Round to nearest is one, but there is round down, round up, round towards 0. So do you anticipate a developer to develop a correctly rounded function for each of these rounding modes? And further, if you look at the machine learning literature, so every vendor has their own representation. Like Google and Intel have bfloat 16, NVIDIA has TensorFloat 32, which is a 19-bit representation, and then there is a P3109, which has an 8-bit floating point representation. So effectively, like the throughput, like the amount of memory, amount of data transfer that you need to do with like 32-bit and 64-bit representations becomes exorbitant when you're looking at trillion parameter machine learning models. So you want like a succinct, like an representations, and you will trade off some precision, but like you want to represent them with the way it's succinctly as possible. And some people, some folks even do quantization and like reduce everything into 4-bit integers. So now, if you are a library designer for a large compiler or a mainstream library such as LLVM, what do you do? You don't want to design a custom function for every rounding mode and every representation. Their suggestion was, can you generate a single implementation that magically works for all representations and all rounding modes? This was a suggestion long time ago, and then we started thinking. Okay, so the question that we set out to think is, how do we produce a single polynomial approximation that produces correctly rounded result, not just for one representation, but for multiple representations and multiple rounding modes? So what would you do? Like, let's say you are entitled with this task of generating a correctly rounded library that works for multiple representation. So if someone says, okay, the largest representation that I'm going to use is a 64-bit representation, so you invest all your energy in developing a correctly rounded result for a 64-bit library. Now you have and then you repurpose it to use it for other representations. So let's say you want to produce a correctly rounded log x for a 32-bit representation. What would you do? You have a correctly rounded 64-bit library. You take an input in 32-bit. You promote it to an input in double. So there is no loss of information here, because every input that is representable in 32-bit float is also representable in the 64-bit doubles. And then you call the library. It's a correctly rounded library. It produces the output y in double. And now you round the result to float. Okay, so this is what you would do if you don't have access to custom libraries for 32-bit, but you have invested all your energy in generating a correctly rounded 64-bit library. But this produces wrong results. And in the numerical methods world, this is due to double rounding. So what is double rounding? So there was first rounding that happened when the math library was generated. You generated it with like infinite precision and with the best known algorithm, and then you did one rounding to the target representation. The second rounding happens when you take the result of the math library and round it to the target representation here to float. And if you're writing any high performance numerical code, double rounding is one of the things you worry about all the time. So just to illustrate this point, I'm showing a cartoonish figure where like the first, the bottommost row is a 32-bit float values, and the first row are 64-bit double values. So for the purposes of exposition, I'm showing like there are 3 values between 2 adjacent 32-bit values, but there are like millions more values between millions of 64-bit values between 2 32-bit doubles. So let's say star is your real value produced by your math library. It's correctly rounded for 64-bit, so it produces the correctly rounded double result, the green dot, but it's exactly at the midpoint. And now it rounds to the red square as shown, which is incorrect, because if you look at the star, it is less than the midpoint. It should have rounded to the blue square as shown. So this is double rounding. The first rounding happened when the star was converted to the green circle, and the second rounding happened when the green circle was rounded to the red square. So double rounding changed the rounding decision. And why did this happen? The intermediate result, the green circle, lost information about the real value. It did not maintain all information about the real value. So, and this is why double rounding changed the rounding decision and caused errors. So our idea in the LLVM approach is, so we want to generate correctly rounded results for multiple representations and multiple rounding modes with a single polynomial approximation. Okay, so we have to do double rounding. Double rounding is necessary because otherwise you cannot have a single representation that produces correct result. But what we really need to do is to make double rounding harmless or innocuous. And now I'm going to describe our magic solution to accomplish this. And then what I'm going to do is I'm going to walk you through why does this solution work? Okay, let's say you want to generate correctly rounded results for all representations from 1 to 32-bit and with all the rounding modes in the IEEE standard. So I want to generate correctly rounded results for all representations between 1 to 32 bits and for all inputs in those representations and with all the rounding modes. Our idea is, what is our magic idea? Create a polynomial approximation for a representation with 2 additional bits. Okay, so we want to generate correctly rounded results from 1 to 32 bits. So we'll create a polynomial approximation for 34 bits. And then what rounding mode do we use to generate this polynomial approximation? We are going to use the rounding mode known as round to odd. And when you create a correctly rounded math library for 34 bits with the round to odd method, and when you double round the result, it produces correctly rounded results for all representations from 1 to 32 bits with all the rounding modes in the standard. And so what is round to odd? So there are a lot of things to parse, and why does this work? We will walk you through each of these steps. So the first thing is, what is round to odd? So round to odd is a non-standard rounding mode. We did not design it. It's been there. There are references to it, like various parts in the literature on floating point, like starting with John Newman's like initial expose on the EDVAC and the ENIAC systems. So what is round to odd? Let's say we just have integers. In our world, we don't have any fractional numbers. We just have integers. And you go to a restaurant, and it turns out your bill happens to be 10.3, $10.30. And now you don't have 10 fractional value, so you need to round it. So where do you round? With round to nearest, we would have rounded it to 10. But what does round to odd say? If a value is exactly representable, then it rounds to that value. If it's not exactly representable, you round to a value, nearest value that is odd. So 10.3 would round to the nearest value that is odd, that is 11. Okay, so 10.3 is not exactly you round it to 11. And similarly, you get a 9.8. So 9.8, what is the nearest value that is odd? It's 9. So it rounds to 9. A 10, you get a value 10. It's exactly representable in your representation. It rounds to 10. So what we showed, to correctly round any real value to any target, you need 4 pieces of information. Okay, what are those 4 pieces of information? Is the value at the midpoint? Is the value less than the midpoint? Is the value greater than the midpoint? Or is the value exactly representable? And what we show is round to odd preserves exactly this information. So hence, rounding any real value to any target is same as rounding the round to odd result to any target. So I'm going to illustrate round to odd with an example. So let's say we have a 34-bit IFP representation. So if the value is exactly representable, those diamonds, it rounds to that value. If a value is not exactly representable, okay, so that such as a star, it rounds to an adjacent value that is odd. So now, why does round to odd make double rounding innocuous? So I'm going to illustrate it with an example. So here, in the first row, in the bottommost row, I have 32-bit floating point values. So some bit patterns in 32-bit floating point are even, and some bit patterns are odd. Okay, so just for the sake of exposition, let's assume the leftmost value in this 32-bit representation, 32-bit float is even. Okay, so when you create a 34-bit representation, any value that is representable, any value that is representable in 32-bit float is even in a 34-bit representation, and the midpoint is also even in a 34-bit representation. Okay, so if the value is exactly representable in 32-bit float, it will be even in 34-bit, so it rounds to that value. Okay. If there is any other value which is not exactly representable, so then it rounds to a value which is odd. Okay. Here there's a star. It rounds to the green dot. And now when you take this green dot, it maintained the information that this value was less than the midpoint. And now you take the round to odd result and round it back to the 32-bit result, it still works out of the box. It produces rounds to the correctly rounded 32-bit result. So we did double rounding, but still maintained enough information about the real value, whether it's less than the midpoint, equal to the midpoint, or greater than the midpoint in your round to odd result, so that you may double rounding innocuous. This was our insight. So why hadn't anyone used round to odd to generate math libraries? Because the community had been focusing on building correctly rounded math libraries by approximating directly the real value. They never focused on the rounding mode. But in our case, we always thought, oh, that directly approximate the correctly rounded result. And when you have a correctly rounded, you are generating a result with respect to the specific rounding mode. And all our techniques were designed with a rounding mode in mind. So now we generating round to odd result was very straightforward with our technique. So hence RLLVM using round to odd with RLLVM approach is very straightforward. Okay. So now what is the methodology for generating a single polynomial approximation with RLLVM approach that produces correctly rounded results for multiple representations? As before, use an oracle to generate a correctly rounded result for a representation with 2 additional bits, which is 34 bits, with a round to odd, that's with a correctly rounded round to odd result. Okay. And then you compute the rounding interval for each of these inputs. So one thing to note when you generate the rounding interval for round to odd results is there are some results for some special cases, the rounding interval is a singleton. So if the output of an elementary function happens to be an even value, it's exactly representable and it's an even value, then it's a singleton. For example, if you're approximating log x to base 2, and x happens to be a power of I, 2 to the power of I, and I is even, then it's a singleton. And designing polynomial approximations with singletons is challenging. So we use certain numerical properties of the elementary function. When is the result of an elementary function exactly representable? These are irrational values. It should be rational values in 99.99% of the cases. Only in some cases, there'll be rational values. We use those properties properties of these functions to identify them and filter them out. Okay, there are fantastic results from Lindenman showing this when such functions produce rational values. And if you filter them out, you're left with rounding intervals. For the other functions, we generate a polynomial approximation as before with a system of linear inequalities. And there you go. You now have a single polynomial approximation that works for all representations and all rounding modes. Okay. So I went back, gave a talk again to the mainstream developers. They said they were excited. Oh, now you have a single polynomial that produces correctly rounded results for all representation. This includes B float 16, tensor float 32, and 32-bit float. One of the developers said, oh man, but you're making every representation pay the cost of the largest representation that you have. Like you generate a polynomial with k terms, everyone is paying the cost of generating the correctly rounded result for 32-bit. So can you make B float 16 or tensor float 32 faster while having this property? This was a suggestion again. So then we thought hard and we came up with this idea called progressive polynomial. You have a single polynomial, you evaluate all the terms, it produces correctly rounded results for all representations. And for some representations, such as B float 16 or tensor float 32, you just evaluate the first 3 terms or first 4 terms of the polynomial. It produces correctly rounded result for that representation. And with our approach, doing this is just adjusting the constraints. You'll have more constraints. Okay, so now one of the things I've alluded till now is, you have to solve the system with 4 billion constraints. How do you to generate these polynomials? How do you solve them? And when we actually try to use existing solvers, they all would time out with these with these systems with 4 billion constraints. So the first thing that we observed to solve them is the system of linear inequalities that we have is a system of low dimensions. Even though we have 4 billion constraints, we don't have 4 billion variables. We have like 5 to 6 variables. So there's a lot of redundancy in the system. So our idea is if you have a feasible linear program with 4 billion constraints and a very small number of variables, this is low dimensional, there are like k key constraints. You identify them from this entire universe and you design a solution for them, you'll solve the entire universe. So now the question is, how do you identify these k constraints and how do you generate a solution? You can't give the entire 4 billion constraints to CPLEX or SOPLEX or Gurobi or any of your favorite solvers. They all time out because they are optimized for this scenario where like the number of constraints is equal to the number of variables, they run out of memory. So inspired by this fantastic algorithm by Clarkson from the Journal of the ACM 95, we designed a class of Las Vegas algorithms. So what we do is we're going to do weighted random sampling. So what do we have? We have 4 billion constraints. We want to identify the k key constraints, where k is the number of terms in your polynomial, number of coefficients that we need to generate. And you solve them, and you will be able to produce a solution for the entire system. So initially, we don't know which constraints are important. And if you give the entire system to the existing solver, they time out. So we are going to do weighted random sampling. Initially, we are going to assign a weight of 1 to all the constraints. Okay. So and then we'll get a sample. We chose some sample. The blue points are the sample points. How many sample points are we going to choose? We are going to choose 6k square samples, 6k square constraints in the sample. What is k? K is the degree of the number of terms in the polynomial. So let's say you're looking for a polynomial of degree 5. So there are 5 terms. So 6k square would be 6 times 25, which would be 150. And we generate a sample. You give us 150 constraints to any mainstream solver. It will generate a solution. And now we check if the sample solution satisfies the entire universe or not. Some of the constraints will be satisfied. Others will be violated. The blue constraints are the sample constraints. The green constraints are the constraints that are satisfied by the sample solution. And the red constraints are the constraints that are violated by the sample solution. And now what are we going to do? We are going to double the weights for each of the violated constraints. So the whole hope is in the next iteration, we want to, when we do weighted random sampling, we want to choose the violated constraints. Okay. So now we're going to sample according to the weights again. And it will satisfy some other constraints, and some other constraints will be violated. We double their weights, and we repeat the process again. Okay, and now we chose another sample, and it satisfied all the constraints. Our PLDI paper gives the proof that this algorithm for a feasible linear program of low dimensions, it generates a solution in 6k login iterations. So to put everything in perspective, directly approximate the correctly rounded result, create a rounding interval. Now you create a linear system with 4 billion constraints, solve this linear system with our algorithm. There you go, you can generate a correctly rounded math library. This is all theory that I described for a long time. Does it work in practice? So we have developed RLBAN, which is a collection of math libraries. A single polynomial produces correctly rounded results for all inputs and for multiple representation, 805 such representations with a single polynomial. And just to compare with mainstream libraries, like we have glibc float, Intel's float and double libraries, they all produce wrong results for some input or some representation. So maybe we are paying in terms of performance. Now I'm going to show how much faster our functions are compared to Intel library. So 1.0x means like we are as good as Intel library. If you have a bar that is 1.5x, that means we're 50% faster than Intel's library. On average, Intel's float functions, if you just use the floating point representation to generate the floating point math library, so Intel has those functions. Compared to them, we are about 30% faster. Intel's functions are like have produced wrong results for more than millions and several million inputs, but we produce the correctly rounded result and are faster. And when you compare to double functions, Intel's double functions, the Intel's double functions are a bit more accurate than float functions, but still produce wrong results. We are 50% faster than Intel's double functions, and while still producing correctly rounded results for all inputs. And now maybe if you compare it to other correctly rounded libraries, CRLibM is a 64-bit correctly rounded library. We are almost 3x faster than CRLibM. Okay, so the moral of the story is you can both be fast and correct if you use the RLibM approach. So one of the gratifying features of this work has been now there is a movement to make correct rounding a required thing in the next version of the IEEE 754 standard. 5 of the functions that we built using libc are now few of 5 of the functions that we built in RLibM are now part of LLVM's correctly rounded functions. And I'm part of the standards committee. So we are making a case for, we have a group item on making correct rounding mandatory in the next version of the IEEE 754 2020 revision. So to conclude, like what there are 3 main points that I want you to take away. 1, directly approximate correctly rounded results. So take a contrarian approach. Sometimes like rather than thinking like a mathematician, thinking like a computer scientist is really useful. Once you approximate the correctly rounded result, there is a rounding interval around the correctly rounded result. It induces a linear constraint. Solve a linear program, you develop a correctly rounded library. You can make double rounding innocuous and generate a single polynomial that produces correctly rounded results for multiple representations. The idea is create a polynomial approximation that produces the correctly rounded result for 2 additional bits with a round to odd mode. It makes double rounding innocuous. So again, these are basic initial few steps in making correct rounding mandatory in the next version of the standard. The goal is to make our scientific software machine learning code more reproducible and portable going forward. Again, I just want to advertise, I'm just advertising the work. My students do all the cool stuff. These are the graduated students and the current students who have contributed to the project. My group has a lot of other research on security, formal verification, eBPF. If you're interested, look at the webpage. Thank you for your attention. All our prototypes are available open source.
Thank you so much, Dr. Santosh, for the fascinating topic that you talked today. So I think now we'll leave the Q&A sessions, and while we gather the questions in the chat, maybe I'll start with some questions. This is not my area, so forgive me if I'm asking. Is there a reason why you chose a progressive polynomial, and is there a reason, can you
so effectively, like when we generated RLibM, right? So we had a single polynomial that produces correctly rounded results for all represent 32-bit, 16-bit float, half precision. So when I gave this talk at, I think, Google, and like one of the Google developers, like they really wanted bfloat16. If you want just generating a library for bfloat16, you don't need like a polynomial of degree 13 to approximate sign. You can do it with degree 5. So, but the trouble was, like now, like you'll have to have a separate polynomial for bfloat16, separate polynomial for 32-bit float, separate polynomial. RLibM avoided all this. So the whole idea with progressive polynomials was you still have a single polynomial that produces correctly rounded results for everything. But now let's do a favor for bfloat16 users by just using the first 2 terms or first 3 terms of the same polynomial to produce the correctly rounded result. So like so producing sine of x for with bfloat16 does not require you to compute like 14 terms, and each term has x power 13, right? So you can just use first 3 terms and you have the correct result. That was the intuition for progressive polynomials.
You probably have addressed this. I think one of the lower bit width, is going to have an implication on the cost for larger representation, right? I think you talked about some on that context. So moving forward, what is your, research is going to be now that you have both accuracy and also faster representation, faster speed in some of these functions that you talked about. So What is your, takeaway from extending this work, and what is your plan?
So that's a great question. So as I said, this is just the tip of the iceberg, right? Math functions are like, these are primitives. Like, it's just like you're building a house. You got your copper plumbing right, but your house is not ready, right? Like, you still need to get like you need to get the joists done. You need to get the beams done. So what are those to build like numerical code? Like, for example, if you want to do gradient descent, right? Like, some of you might have seen the Sora video. OpenAI released this fantastic LLM generated video, right? And if you carefully look at this video, it looked like animation rather than a real video. Why? Because it was not taking physics into account. And to do realistic real world stuff, you need to model physics.
Mhm.
And now when you're modeling physics, like the way you do this is with a kind of solvers called as Kirchhoff subspace solvers. You're solving a large linear system, but like now you're developing class of iterative methods to do that. How do you reason about these iterative methods and correctness? And these algorithms were developed 60 years ago. They terminate with real numbers. But when you do it with floating point, no one knows why they were. So how do you systematize and mathematize? Like, so physics, real math is going to be cornerstone of our daily life going forward, with so much integration of machine learning models and everything. So how do you make these systems robust, which was like primarily restricted to a very small group of people who would do combinatorial optimization or numerical methods. Now, like, these are like the doctors you need every door, right? every street, right, to make our system safe. So I think like one of the things I want to advocate with this talk is the community should pay attention. Like, now we need people who are like conversant with these techniques to advance, to make like take AI to the next level, right? Like, you want like the AI methods to be deployed in critical systems. Reasoning about them is very important, and building strong foundations is important. And what we have done is just like basic call to arms kind of work, rather than solving this problem once for all.
Thank you. If you don't mind, if we can go back to slide 80, I have a question on those, you had some certain functions like sine, edge, cosine, has much more, the speed is faster in those functions versus the other ones that I see in the front, right? I think if you, in your slide, and,
80?
Yeah, slide 80, I think. Yeah. Oh,
Yeah,
okay.
on slide 80.
So I'm just looking at a practical use case. For example, there are, federal agents like DOE look at practical applications of use cases when you look at, for example, electric grid time series data, right? So which are trig functions representations, in some way, I think, so the question here is, you talked about, areas where, correctly rounded approximations makes a big impact in certain use cases. There are different applications are very critical to follow certain things. And I'm just looking at, not on the foundational aspect of improving this, and I'm looking at use cases for this, the question I have is, do you see any significant performance on round to odd versus round to even, when you see some representation on these high level, the sine H, cosine, sine pi, cosine?
Okay, so I think like I want to get two things clear. Round to odd is an internal idea used to generate correctly rounded results for all representations. So that is just for the purposes of generating the library. So like, a user does not worry about round to or whatever. I, as a mathematics LLVM designer, I think about round to odd to generate this polynomial approximation. The user, they use their own rounding mode, round to nearest, right? For them, this is what the speed up that they see. So let's say you have an application, a gradient descent algorithm, and you're repeatedly calling e power x in your internal loop. And you use an intel library with whatever rounding mode, round to nearest tries to even, or round up or round down, whatever is specified in the standard. Use it. Your application is going to be about 50% faster by using our library while being portable and correct. So all we are saying is you're already using incorrect libraries, which are slow and incorrect. Now just use RLLM. It's correct and it's portable, because like now you can take this code, run it on AMD GPU, Intel GPU, or an Intel CPU or AMD CPU. They all produce the same result because it's correctly rounded.
How is your reception from these companies, when you talk in these libraries? I'm just curious to see, hey, they must be,
Yes. So I think like I'm collaborating with Intel right now. So for example, Intel internally is using our LLVM functions. So Intel has been a generous funder of my research for the last 4 years. I'm collaborating with the Intel LLVM designer, Marius Cornea, and various other people. Internally, Intel is also developing like correctly rounded functions and evaluating using our LLVM as a benchmark. So again, I want to emphasize that RLLVM is not the only correctly rounded library. There is a parallel effort by Paul Zimmerman at INRIA. It's called the Core Math Project. They have a correctly rounded elementary functions too. So we together as a team are now making a case. So in the next version of the C standard, next version of the floating point standard, any hardware that is compliant with this standard has to provide at least one correctly rounded implementation. So now the onus is on the user. They want to be incorrect and fast and non-portable. They can choose an incorrect version. And if they want to be fast, correct, and portable, they can choose a correctly rounded version. So there is no free lunch. There are in some domains that you may have to pay a small price for correct rounding. So, but we leave it to the domain experts to make the choice. But right now, we are in the current state of the art, like at least like when we started this project 6 years ago, there was no correctly rounded function available. So even if the user wants correct rounding, I want portability, there was no option for them. So at least what we have done in this project, like what I'm proud about, is at least got the community's attention. Like there are people who care about correct rounding, people who care about portability. At least they get a say in the room now. They can use this library.
Fascinating. I think that's interesting. I think kudos to your team and the effort what you guys are doing. One final question in terms of security perspective, right? How do you see this? How do you see your work, making an impact from the security work, and I'm just, we don't have, when I work with a lot of DOE companies and energy companies, do we have an agreement on this so-called, what is the correctly rounded thing mean, and everybody has, is there any standard that's going to drive, hey, maybe, I don't know, I'm just curious to see.
Yeah, so I think security is a very interesting thing. So there are like, in general, again, there are a lot of things to think about security. When you use a finite precision representation, you're making an approximation. You want to ensure that your approximation is not going to result in a catastrophic failure. So there have been like well-documented instances of failure, right? Like for example, some of the Pathfinder missions failed because of the cache from 16-bit, the domain, the data representations were not thought about. So you had an overflow. And people already know in the security world why integer overflows are bad, from how an attacker can just take control of your system with a single integer overflow, a collection of integer overflow by designing careful gadgets, right? Even from a floating point perspective, right? Floating point representation has subnormal numbers or denormal numbers. And many a times, denormal numbers are like emulated rather than directly implemented in hardware. Like so because the people think, oh no, denormal numbers don't arise so often in practice. So there is a cool paper a couple of years ago, subnormal numbers and their abnormal timing. Very clever pun on the title, but I think like they were saying like how you can use subnormal or denormal numbers to generate timing attacks. So I think so what is security, right? Absence of a safety property. Absence of safety means you will violate an internal invariant. And now when you violate an internal invariant, you are now creating an attack surface for anyone to exploit. And now what the security community has shown, you give an inch to an attacker by exposing your attack surface. There are like really talented attackers out there who will take control of your system. So I come from the formal methods world where like I value safety. So don't give an inch to an attacker to exploit. It's a delicate game, but I think rather than primarily thinking about correct rounding, think in terms of data representations. If you violate the invariant of your data representation, you create an attack surface. So how do you train next generation of security analysts to think about data representation, think about number representations critically so that this violation of safety invariants don't happen and create a security vulnerability eventually? So that would be my perspective.
Yeah, that's very interesting. I think there's more room to progress on that direction for research. Yeah. Thank you so much. I think I don't want to take too much of your time. I think you will receive a nice plaque from UND, as for your contribution for this webinar. We'll make a recording link available and share it with you so you can able to promote, for any ways you can. Thank you so much, Dr. Santosh, and let's find ways to work together and see if we can able to.
And then thanks again for the invite. It was a pleasure talking to you, and thanks for the really interesting questions. And I look forward to talking more and like discussing research in the future.
Thank you.
Thank you.
Take care.